Hi, my name is Y-Team and welcome to Statistics 101 from scratch in Python. In this lecture, we cover undergrad level statistics, providing easy to understand intuitive definitions, plenty of examples, and Python code for replication and application. The table of contents are as follows. We first cover statistical measures, which includes topics like mean and variance. Next, we briefly touch upon basic mathematical concepts that are used in future topics such as matrix, error function, and calculus. We then discuss statistical distributions and their relationships. There are 9 statistical distributions covered here, which are Bernoulli, binomial, normal, t, poisson, exponential, gamma, chi-square, and f. Finally, hypothesis testing is covered where it looks at mean, variance, difference, and ratio. Additionally, ANOVA, goodness of fit, contingency table are discussed, which are also important topics that will come up in more advanced statistics. Requirement of this lecture is somebody who has finished high school mathematics with medium retention. Endurance to carry on, finish the entire lecture. Python knowledge is good to have, but if you are new, any 1 hour basic lectures available in YouTube will suffice as you take this lecture. Most importantly, a proactive and curious mindset is required. Target audience are either students or industry professionals. The objective of this lecture is to provide the best possible lecture to achieve the following. First, understand concepts in statistics and econometrics in a holistic manner, such as what is the relationship between Poisson, chi-square, and normal distribution. Second, understand the concepts both in theory and intuitively based on mathematical proofs, practical example quizzes, and construction from scratch through Python simulations. Why divide by n-1 for sample variance? And when can I use Poisson distribution to model practical ideas? Third, get enough hands-on experience in coding statistical and econometric concepts so you can easily apply to new data sets and further think of creative modeling techniques. Fourth, reach the level of understanding that allow you to be able to teach to another person. Lastly, solid foundation to more advanced topics in statistics and econometrics. Let's first go through definitions. The expected value of x, mean, is calculated as weighted average of possible values of x. Next, variance is defined as the expected value of the x minus mean squared, meaning it can examine the same population numerical measures for samples. In real life, it is hard to deal with the entire population. When we want to know the statistics of students' weights in a classroom, it is easy. We can simply measure everybody's weight. But if you want to know the statistics of weights of the entire city or a country, sampling is necessary. Let's start with mean. Here, mean is calculated the same way as the population mean. Important to note that we are using the notation x bar, not mu. This is because x bar is not a constant. Mu is a specific number, but x bar is a variable that will change depending on the sample. On average, x bar is same as mu, but it does have variance of sigma squared over n, where sigma squared is the population variance and n is the sample size per independent trial. If you don't understand this, go back to review the quizzes of stock yearly standard deviation example and exponentially weighted mean of white noise example. Next, variance is defined as sum of x minus x bar squared divided by n minus 1. Why n minus 1? Let's break it down step by step, comparing with how population variance is calculated. So we define variance as how much x deviated from its mean. However, key difference is that for population, mean is known. You simply do an average over the entire population, while for sample mean is estimating using the average of the samples. So in the second row, for population expectation of mu squared is simply mu squared. For expectation of x bar squared, it is average of x bar plus its variance, which is mu squared plus sigma squared divided by n. Looking at the last row, for example, we get n over n minus 1 times sigma squared, meaning we are understating the variance of the population if we use only the samples to calculate it. This is why we divide by n minus 1, not n, to account for the underestimation. In statistical terms, we use n minus 1 for unbiasedness. Intuitively speaking, the difference comes because x bar is not a constant. Volatility is embedded to x bar. So whenever we draw samples per trial, x bar shifts to the average of x is drawn, reducing the volatility slightly. For skewness and kurtosis, it will be enough just to take a look. No need to memorize. However, idea is the same. This part should be a reminder for those who have good memory retention from high school. But if it sounds new to you, it's not a problem. You can follow along and revisit here whenever these concepts pop up in the later stages of this lecture. I will not cover parts in the PDF that you can just read through. Let's now review and solidify what we have learned through a coding session. First, through Python simulation, we can show that variance of x equals expectation of x squared minus mu squared. As you can see, this does not follow any known distribution, yet the relationship holds. Next, we can show quiz 1 using Python. Given a and epsilon, we can set small a and b in a following way to make a new series B that has correlation of 0.5 with a. Additionally, it can be shown that the standard deviation of a plus b is less than the sum of each of their standard deviation. This is true because correlation of a and b is less than 1. This is a plain example from quiz 2. We can see that the average of squared values is equal to the square of average plus the variance. We can also check visually why this makes sense. Here we show that x and x squared are uncorrelated but not independent. Using simulated x values, it can be shown that x and x squared are uncorrelated with a very small correlation value. However, probability of x and y being above 1 is larger than the product of each one being above 1. This is because the two are related. From quiz 3, we show that if each daily return is uncorrelated and given trading days of 252 a year, yearly standard deviation is around 16, which is the square root of 252. However, this is assuming additive returns. If we look at cumulative product, the yearly standard deviation is much less, around 11.5. Quiz 4 shows effect of exponential moving average and its effects on the variance. We can test this out using simulation generated from quiz 3. This is simulated test of quiz 5. We can see that 3 values roughly match. This one shows using simulation why when we use samples, to calculate the variance, we need to divide by n minus 1, not n, so that we don't underestimate the variance. In this code, 1,000 simulations are done. With given trial, 5 samples are picked from the population. The population variance is around 1, but the sample variance that does not divide by n minus 1 gives variance on average about 0.5, 0.8, which is much smaller. This point shows Euler number used in continuous compounding context. 1% on a continuously compounded terms yields e to the power of 0.01, which is approximately 1.01005. So let's get back to statistics. There are many distributions discovered by statisticians. Below are some selected essential distributions I will cover. We can broadly divide into discrete and continuous distributions. Discrete distributions include Bernoulli, binomial, and Poisson. And continuous distributions include normal, students t, exponential, gamma, chi-squared, and f distribution. So total of 10. I will give the definition from Wikipedia and the formula. First is Bernoulli distribution. This is a discrete distribution where the random variable x can either have 1 or 0 as a value. And probability of x equals 1 is p, and x equals 0 is 1 minus p, which is denoted as q. Expected value of a Bernoulli distribution is p, and the variance is p times 1 minus p. Example of this is a coin toss where p is 0.5 and head corresponds to 1 and tail corresponds to 0. Second, binomial distribution is a discrete probability distribution of the number of successes in a sequence of n independent Bernoulli events. This is equivalent to multiple coin tosses, asking, given n coin tosses, how many heads I get. Expected value of a binomial distribution is NP, and variance is NPQ. This is used when we talk about confidence interval of election polls, which I will discuss in later coding session. Third, normal distribution is the most famous continuous distribution that has the following probability density function. More specifically, any normal distribution can be standardized by subtracting mean and dividing by the standard deviation to get standard normal. If you remember variance formula, it is easy to realize that dividing by the standard deviation will get you a distribution where variance is 1. One of the main reasons why this is important is because of the central limit theorem. Central limit theorem proves that the sum or average of random variables from any distribution, if independently drawn, will approach a normal distribution when n approaches infinity. Looking at this formula, say x has mean of mu and variance of sigma squared. Note x can follow any kind of distribution shape. As we learned before, 1 over n times x follows mean of mu and variance of sigma squared divided by n squared. Summing this up, variance is additive as we are assuming independence, meaning zero correlation. Variance is now sigma squared over n. To make the variance to sigma squared, we multiply by square root of n. Because of this property, normal distribution tends to appear more often than other distributions. So it is nice to remember some properties of normal distribution. Within plus minus 1 standard deviation of a normal distribution, probability is 68%. Plus minus 2 standard deviation is 95%, and 3 standard deviation is 99.7%. Another thing to note here is in this graph is at x equals 0, PDF value is around 0.4. This does not mean that probability of being at the mean is 40%. It just means that the derivative is 0.4. In a continuous distribution at any given number, the probability is a very small number. So at 0, it would mean 0.4 times dx, where dx is a very small derivative. Binomial distribution will approach to a normal distribution if p is around 0.5 and n approaches infinity. You can tell from the formula that in binomial distribution, as n becomes larger, skewness and excess kurtosis approaches 0. One interesting fact about binomial distribution is that as n increases, the excess kurtosis actually increases from a negative number to more closer to 0, which is the excess kurtosis of normal distribution. This might sound counterintuitive at first, but you can think of it as when n is too small, it is just not enough trial to have tails in the first place. For skewness, you can see if p deviates to the upside from 0.5, it will have negative skew, but will come closer to 0. And as n becomes larger, and on the other hand, if p deviates lower from 0.5, it will have positive skew and will become closer to 0 as n becomes larger. I'll give two examples. First example, given trial p is 0.55, what is the probability of x larger than 60 given 100 trials? The exact formula would be the following, which gives 13.43%. We can approximate this using normal distribution. Standardizing, we subtract by NP and divide by square root of NPQ, and we get 15.74%, which is roughly a similar value. Second is related what we often hear during election seasons. When the article says the polls have confidence interval plus minus 2.5% points and 95% interval, what would a rough estimate of how many people it surveyed? Using binomial variance formula, we can estimate the variance, which is NPQ. Here we are dealing with ratio. So variance of x over n is PQ divided by n, where n is the number of people surveyed. For many polls, they use 0.5 for P, as this is what would maximize P times Q, just to have a conservative estimate. And as we already know, plus minus 2 standard deviation range is 95%. So the following equation should be equal to 0.025, which means n is equal to 1600. Fourth, students' t-distribution is a distribution that comes into play when estimating the mean of the population using a small sample size drawn from normal underlying distribution. If you have too small a sample, typically rule of thumb is n less than 30 samples for central limit theorem to apply, and you do not know the population standard deviation, t-distribution is used. In this case, t-distribution would be best used when underlying is either approximately normal or normal. In a case where sample size is large enough, since central limit theorem applies, regardless of if you know the population standard deviation or not, you can use the normal distribution. Lastly, if you know the population standard deviation and underlying is normal, you can use normal distribution for estimating mean of population with samples, even if sample size is small. So in summary, when underlying is approximately normal, but you do not know the population standard deviation and sample size is relatively small, you have to use t instead of normal distribution. There is uncertainty coming from the estimated standard normal. In t-distribution, nu refers to degrees of freedom, which is equal to n minus 1, and n is the sample size. See from the formula that as sample size increases, variance in excess kurtosis comes down to 1 and 0. We can see that when sample size is small, it has fatter tails compared to standard normal distribution. Fifth, Poisson distribution is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time or space if these events occur with a known constant mean rate and independently of the time since the last event. So, for example, if bus arrivals follow a Poisson distribution with mean of 5 over 1 hour, it means on average over 1 hour period, 5 buses will arrive and probability of future bus arrival will remain the same whether the bus has just arrived or not. Looking at the formula like t-distribution, it is entirely defined by degrees of freedom parameter nu. Poisson distribution is entirely defined by the lambda parameter. Mean and variance is equal to lambda, and as lambda increases, positive skew and excess kurtosis approaches 0. We can look further into Poisson distribution by looking at its relationship to binomial distribution. Binomial distribution approaches Poisson distribution when n goes to infinity, but p goes to 0, while n times p stays constant at lambda. You might wonder if binomial distribution approaches Poisson, why does binomial distribution have variance of npq, while Poisson have variance of np? This is because when p goes to 0, p times 1 minus p is basically p times 1. So npq is equal to np. Poisson approximation is reasonable in the case where n is larger than 50 and np is less than 5. First example, let's say a casino slot machine has a jackpot probability of 1 over 10,000. If the slot machine was pulled 5,000 times, what is the probability that will be 3 jackpots? The exact probability can be calculated using binomial formula. The probability of getting 3 jackpots equals 5,000 combination 3 times 1 over 10,000 to the power of 3 times 9,999 divided by 10,000 to the power of 5,000 minus 3, which is approximately 1.2632. Since 5,000 is a large number and probability of getting a jackpot is small, given trial, we can approximate it using Poisson formula. Lambda, which is the mean, equals 5,000 times 1 over 10,000. x in the formula equals 3. So this yields 1.2636, which is a good enough approximation for most cases. What is good about this method is that below formula is more computationally efficient as compared to above, where you have to multiply 5,000 times. Second example, a stock index have a strong correction on average once every 2 years. What is the probability of there being only one correction in 2 years? This is straightforward. Average lambda is 1, x is 1, and putting this into formula, this yields 36.79%. This can also be approximated with binomial formula where 730 is equal to 2 years and gives a similar value of 36.81. Then how would you calculate one correction in 1 year's time? You might be tempted to think one correction in 1 year is equivalent to 2 corrections in 2 years, so you calculate it using lambda being 1 and x as 2, giving 18.39%. Alternatively, you can say average of 1 per 2 years means 0.5 in 1 year, so lambda is 0.5 and x is 1, giving 30.33%. In this case, latter makes sense, not the former. This is because the time frame we are interested in is 1 year, not 2 years. And the shape of the distribution changes as time passes by, although given date, the correction probability remains the same. So if you were to calculate lambda set to 1, you are using the wrong distribution. Let's try another one. Say, what is the probability of there being only one correction in 3 years? Then lambda is 0.5 times 3, so 1.5, and x is 1, giving 33.47%. You can see this from this plot. While the probability given a small period, in this case, small period meaning a single day, remains the same, as the time frame expands, the distribution changes. So it is important to think in terms of the right time frame, meaning the right distribution. Third example, bus arrives on average 6 times per 1 hour. What is the probability that at least 2 buses arrive in 10 minutes? Given time frame of 10 minutes, lambda is 1. We can get the probability by subtracting probability that 0 to 1 buses arrive. This can be also approximated using a binomial formula. Remember that n needs to be a large enough number so that binomial converges to Poisson. So I randomly select a large enough number of 1000. We get almost the same probability of 26.42%. Fourth example is the same, so I will leave it up to you guys to review. Last example is more related to thinking in terms of actual real world. So assume you start your shift at Starbucks. You were told by the manager that on average you will get around 10 customers in the first hour. 1 hour has passed, and you realize that there has been only 4 customers. Should this be considered an anomaly? If you know the Poisson distribution, you can easily do the maths. The probability of 4 or less customers arriving in the first hour is only 2.93%, given lambda of 10. Of course, the assumption is that we can think of 1 hour as a sum of very small time scales, where probability remains the same given one sub-period. Instead, if we were to think that today's 1 hour is a small sample, variance and tails can be larger as with t-distribution. And in this case, probability of 4 or less customers arriving in the first hour should be much larger and should not be considered an anomaly. Sixth, exponential distribution is a probability distribution of the time between events in a Poisson point process, which is a process in which events occur continuously and independently at a constant average rate. In other words, exponential distribution is the probability that one Poisson incident occurs at x time unit. More simply put, the wait time in time units for Poisson incident to occur follows an exponential distribution. So how do we get the PDF of the exponential distribution? First, set x to the number of time units for Poisson process to occur. Since lambda is average value per time unit, lambda times x is the average per x time unit. So lambda is replaced by lambda x, and second we subtract from 1, 0 Poisson process happening within x time units, which is the following equation. Third, we take the derivative of this equation to get PDF. Lambda times exponential to the power of minus lambda times x. The expectation of x that follows exponential distribution is 1 over lambda, which is what you can expect since given one time frame, lambda events occur. Wait time should be, on average, 1 over lambda. The variance is 1 over lambda squared. And this PDF has skew, and this PDF has positive skew with excess kurtosis of 6. Let's look at an example. Listed stocks on ABC exchange last for on average 10 years until they delist. The lifespan of stocks follows an exponential distribution. What is the probability that a stock will last in between 3 and 11 years? Meaning Poisson hit will occur within 3 to 11 years. Since here we're treating 1 year as a time unit, lambda becomes 1 over 10. Putting this into equation, we do an interval of 3 to 11 time units. And we get 40.79%. Seventh, gamma distribution is a distribution that independent and identically distributed exponential random variables follows. So simply put, it is the time to nth arrival of Poisson process. So while exponential distribution refers to wait time until the first incident, gamma distribution refers to wait time until n incident. Let's look at an example. If stock market corrections occur on average twice over 10 years, what is the probability that 3 corrections or more occur in the 10 years? Easy way to calculate this is using a Poisson formula where we just subtract from 1 0 to 2 Poisson incidents occurring with Poisson lambda equal to 2. Alternatively, we can calculate the probability of wait time being less than one time frame, which is the case for 10 years for 3 Poisson incidents. Both calculations give the same number, 32.33%. Eighth, chi-square distribution with new degrees of freedom is a distribution of a sum of squares of new independent standard normal random variables. Chi-square distribution have mean of nu and variance of 2 times nu. Chi-square distribution is also a special case of gamma distribution where alpha equals nu divided by 2 and beta equals 2. The distributions looks like the following. It is easy to guess that this distribution is useful when dealing with variance. Ninth, F distribution with d1 and d2 degrees of freedom is a distribution of x equals s1 divided by t1 over s2 divided by t2, where s1 and s2 are independent random variables with chi-square distributions with respective degrees of freedom are d1 and d2. You can easily guess that this distribution can be used for comparing two different variants. The mean of this distribution equals d2 over d2 minus 2. The plot shows shapes of f PDF depending on the values of d1 and d2. Also, because of how f distribution is constructed, it has a special property where cumulative probability of f to point x is equal to the 1 minus the cumulative probability of f inverse to point 1 over x. We will check this again in the coding sessions. Before we go to the next topic, let's review some notations used. The letters can be used. The letters used can mean different things depending on what distributions you're using. So try not to get confused. For example, n in binomial distribution is number of trials, while for t distribution, it is number of samples. For x, it means number of successes for binomial, number of occurrences for Poisson, number of time units for one Poisson process for exponential, lastly, number of time units for alpha Poisson process for gamma distribution. Next, let us look at the overview of how all distributions that we have covered are related. If you don't understand any of these relationships, do review, as they will come up again in later topics. One thing we did not cover is that if standard normal and chi-square distribution are independent, standard normal divided by the square root of chi-square over degrees of freedom follows t distribution. There is no need to go down to the numerical proofs. Intuitively, standard normal and t distribution is related, and chi-square term effectively scales the normal distribution by accounting for uncertainty coming from small samples. Now let's go to the second coding session, statistical distribution. This is Notebook for session 2 coding session. These are basic Python packages required to run the following Jupyter Notebook. First, there are two ways to generate a equal distribution, where renint generates integer values and uniform generates continuous real values. Here you see the probability mass function for binomial and can be generated using the stats package. Or you can code it yourself using this kind of function. You can see that whatever you use, the package or the custom-made function, they yield the same values. As we have learned, when single trial, the probability of single trial is around 0.5. As trial increases, in this case 100 trials, the distribution approaches a normal distribution. We can randomly generate a normal distribution with mean 0 and standard deviation of 5 and 1 using NumPy. As with binomial, you can generate probability density function with stats package. Using the cumulative distribution function method, we can see what percentage lies in between standard deviation range. This one shows central limit theorem in action. Any random non-normal distribution, if sample size is large enough, converges to normal distribution. This plot shows t-distribution with specified degrees of freedom. You can see as degrees of freedom increase, the distribution converges to standard normal. Next, we look at Poisson distribution. This is also a discrete distribution. We can see when NP remains constant and n is large, binomial converges to Poisson. This is also a graphical illustration of Poisson probability mass function. We can also use the exact formula as well, instead of using the stats package. These are answers to quiz 8 to 12. So you can review this using these codes. This is how you can generate the exponential distribution, which is basically wait time version of Poisson cases. Based on what we have learned so far, we can analyze real-world data. DF S&P price is a data frame where it has daily price data for S&P 500 from 1945 to 2024. We can see that in general, although not always the case, as we expand the time frame from daily to weekly and from weekly to monthly, the distribution exhibits more normal behavior. We can partly attribute this to central limit theorem in action. Additionally, we can see that over a 5-year time frame, magnitude of monthly returns exceeding 10% has occurred on average 1.4 months and with variance 2.1. We can say that such jumps in returns follow a Poisson distribution. Based on the observation, we can simulate S&P 500 monthly returns. First method is just using normal distribution like DF, S&P month simul, percent simul. Another method is to separate the series into bull and bear markets, where bull market has less standard deviation and bear market has twice the standard deviation of the entire average series, and negative drift in the simulation. We can merge the two together using exponential distribution, where Poisson lambda is 1.4, as we have identified. Then we simply replace the indices where wait time has occurred with the bear markets. Now let's see the actual and the simulated returns. The visual inspection shows that simulated normal plus Poisson is more realistic than simply simulated normal. Although there is room for further modeling to make things more realistic, this is still good given that it only utilizes very basic statistics. This is answer to quiz 13. This shows how you can code gamma distribution. This is chi-square distribution. It shows that under certain conditions, gamma and chi-square are equivalent. Finally, this is F distribution with different degrees of freedom. We can see that because of how F is formulated, we can get the same output using different formulas. There are 6 hypothesis tests we will look at. These involve comparing two values, the value you get from sample and hypothesized value. The first 3 are population mean, ratio, and variance. And there is population mean difference, ratio difference, variance ratio test. Before we go into first hypothesis test, let's review some stats that will be used in this section. If x has a mean of mu and variance of sigma squared, average of sampled n x's, x bar, has a mean of mu and sigma squared over n. We get sigma squared over n because first, sum of n x's will have variance of n times sigma squared. As variance is additive, if each x is independent, and then second, multiplying that by 1 over n will get you n sigma squared divided by n squared, which gives you sigma squared over n. Next, if x has mean of np and variance of npq, x over n will have mean of p and variance of pq over n. I'll pass the next row for you to just have a look. Next, when x follows a normal distribution with mean mu and variance sigma squared, the samples have mean of x bar and variance of s squared. Then what distribution does n minus 1 times s squared divided by sigma squared follow? If you break this down, we can see this is a sum of n squared standardized sample values. We know that n sum of standard normal values follow a chi-square distribution with n degrees of freedom. However, in this case, as there is variability in x bar, it follows chi-square distribution with n minus 1 degrees of freedom. Lastly, remember that F distribution is related to chi-square distribution in that the ratio of chi-square distribution divided by its degrees of freedom and another independent chi-square distribution divided by its degrees of freedom follows the F distribution. The chi-squared divided by degrees of freedom part can be put as sample variance divided by population variance, which gives the equation shown. These will be used in different hypothesis tests. Let's look at the first one. First is testing for population mean. This is used when testing for hypothesis of the population mean using sample values. In this case, where we want to know the population standard deviation, or we have a large sample, we can simply use the normal distribution. X bar follows a normal distribution with mean mu, 0, and standard deviation of sigma divided by square root of n. We can set alpha to a small percentage, such as 5%, so on either sides of the distribution will be 2.5%. And z value for that meets this condition is plus minus 1.96. So if, say, mu does not fall in this range, we can reject the null hypothesis that mu equals mu0 at 5% significance level. In this case, where population standard deviation is unknown, in the case where population standard deviation is unknown and sample size is too small, we can use t-distribution. Second, we can test for population ratio. For ratios, we can test the formula for binomial distribution. But basically, the structure is the same with the population mean. The ratio follows a normal distribution with mean p, 0, and variance of p0 times 1 minus p0 divided by n, the sample size. Third, population variance can be tested using chi-square distribution. This is intuitive as variance and chi-square distribution both involve squaring. As we have looked before, this requires that sample data comes from a population that follows a normal distribution. As n minus 1 times sample variance divided by sigma 0 squared follows a chi-square distribution, we can rearrange this to get the range for the population variance. If the hypothesized variance falls in this range, we cannot reject the null hypothesis, and if it is outside this range, we can reject the null hypothesis. Fourth, let's look at population mean difference. We can categorize this into 4 different cases. Case 1, known population standard deviation or large samples. Case 2, known equal standard deviation and small samples. Case 3, known unequal standard deviation and small samples. Case 4 is paired samples. First case is very straightforward. The difference follows mean of here denoted delta 0. Usually, since we assume x1 and x2 have the same mean, we set it to 0. And variance is the following. Case 2, we can get the estimate for population variance by calculating degrees of freedom, weighted average of sample variance 1 and 2. For hypothesis testing, we can use the t-distribution with n1 plus n2 minus 2 degrees of freedom. Case 3, if the two distributions have unequal variance, we can just add the two variance to get the variance used in the hypothesis test. For t-distribution, degrees of freedom, the formula is shown, but there's no need to memorize this. Case 4 is a paired case, meaning that the ith, the ith sample in x1 and ith sample in x2 corresponds to each other. In this case, the two are not independent, so variance should be calculated using same sample differences. The rest procedure is the same with population mean hypothesis testing. Fifth is testing for population ratio difference. This is the same with case 1 of the hypothesis testing 4. So I won't go into the details. Sixth is testing for population variance ratio. In the stats review section, we proved that the following form follows F distribution. We can rearrange this to test the population variance ratio using F distribution. I hope all these are pretty clear if you have a solid understanding of stats theory that I have covered. However, if anything is uncertain, we will test this again in the coding session, and everything will become much more clear. Lastly, for statistics, I will introduce 3 additional hypothesis tests that involve comparing 2 or more values. They are ANOVA, analysis of variance, goodness of fit, and contingency table. First, ANOVA is used when you want to compare 2 or more groups. The null hypothesis is that group means are equal. We can check for this by comparing the variance between groups and variance within groups. Variance between groups mean that how do each group's mean deviate from each other. And variance within groups is weighted average of the deviation within each group. So in the case where variance between groups is much higher than the variance within groups, we conclude the null hypothesis should be rejected. As we have learned before, the shown statistic will follow F distribution with number of groups -1 and number of values minus number of groups as degrees of freedom. We test for upper one-tailed test as we want to check for if mean deviates away from each other. The concept of looking at variance between groups and variance within groups does come again in more advanced statistics. So let me digress a bit. Variance of x can be expressed as a sum of variance within groups and variance between groups. The proof goes like the following. As we know, variance of x is the expectation of x squared minus square root of expectation of x. Using the law of iterated expectation, we can rewrite like the following. Next, the blue part can be expanded using the variance definition. We then can see that the second and the third term can be put together as variance of expectations of x given y, which is the between variance. So in the final line, we prove that the variance of x is sum of within variance and between variance. Second, goodness of fit involves checking for if observation is from the expected distribution. For example, say we think population is 50% male and 50% female. And from sampling, we say 51 and 49 male and female. Goodness of fit will tell you if we can reject or not the null hypothesis that 5149 observation comes from the hypothesized distribution. For each observation, we normalize it. In chi-square distribution, mean and variance are equal, hence why the test statistic looks like the following chi-square distribution with k minus 1 degrees of freedom. For example, given k2, k is 2, so degrees of freedom is 1. Note that 1 is subtracted because 51 plus 49 should equal to 100. Third, contingency table involves checking for if there is any relationship between the row and column. The basic idea is that the basic idea is the same with goodness of fit. It just involves more like multiple rows. I will explain this further in the coding session. Now let's go to the third and final coding session for Statistics 101. These first few cells are a review of statistics that we have learned before. Here we generate random variables that follow normal distribution for population mean testing. Population has 10,000 random variables. We sample 100 of them. We can test it using different packages or calculate it ourselves. We can see that all yields the same value, as percent is 77%. We cannot reject the null hypothesis that sample is from the population. Do note that NumPy default is population calculation method, but for pandas, it defaults to sample calculation. We can also do the same for t-distribution test. This shows binomial tests. Next, we look at variance tests using chi-square distribution. These are quite straightforward and shows different formulas all yield to the same output. We now look at two sample tests. Sample A and B are generated. Weight stats provide a simple way to comparing the means. But we can also do a manual way which calculates the same output. Next, we can do a t-test for equal variance and unequal variance. We also have paired t-tests where order matters. Finally, population variance ratio can be tested using F distribution. Now we go to comparing three distributions, ANOVA. Following three variables A, B, C are created. We can test for the null hypothesis of group means are equal, either manually or using the stats package. You can see the manual method and the stats package yields the same output. Additionally, it can be shown that total variance is equal to the sum of within variance and between variance. Next deals with goodness of fit and contingency table, which are quite self-explanatory if you look at the codes. For contingency table, you can generate the expected values given that the row and the columns are related. So this is a way to generate the chi-square test. You can also see that the stats package and the manual method give the same p-value. So this is the end of Stats 101. Thank you for listening this far, and please review this serve as a foundation for econometrics and more advanced topics in statistics.